guys, I sent out the lab for this week. It's a out-of-lab assignment, no lab. Instead, we have a SciFinder assignment. SciFinder is a database for helping you search the literature to help you find references. Okay? SciFinder is not a reference. It's a database to help you find references. Sometimes students will say, my reference is SciFinder. No. SciFinder helps you find references. Okay? Literature references, and it's important to be able to search the literature and then read the literature. So I sent you the assignment. You'll have to log on to the database. You'll need to be on the AU network. Instructions should be clear. There are instructions in the lab manual. Okay? If you have questions, please ask. That will likely be due when you come to the lab next week. Next week we are doing polarimetry lab. Okay? Optical activity of chiral compounds. Questions? Quiz on this Wednesday over alkene reactions, including EZ terminology, nomenclature. How are we doing on nomenclature and EZ? Pretty easy. Question?
When should our lab report, when is it due from this past week?
Bromination lab, a week from today, here in class. What color were the handouts today? One was purple. Okay, 2 handouts today. Stereochemistry, one white and one purple. We'll be getting to that. Stereochemistry, very important. On the back of the white, back of the first page of the white, some D2 questions of the stereochemistry. The first is EZ terminology. Is the alkene in this compound? You ever use stuff like bug spray, home defense? Compound here. Insecticide, alkene. Is the alkene E or Z configuration? There's only one alkene here. These are not alkenes. This is a benzene ring. We do not consider these alkenes. Only one alkene right here, yeah? Cyclopropane, what's this functional group? Yes, ester. Aromatic greens. Alkene is E or Z. It's stereochemistry. Huh? Yeah? Everybody good there? Those are the types of questions that you need to be able to answer. Stereochemistry coming soon. Alkene reactions. Okay, we've got our outline. This Friday I will not be here in class. Instead I did a video covering some of this here. Where are we at? We'll be starting with epoxides. We mentioned that on Friday. We'll pick up there. Using peroxy acids to make epoxides. Cyclopropanes we'll cover today. Check marks. Those are my notes from the video. Oxymercuration, hydroboration, and then hydrogenation covered by video only. Okay? That lecture. 3 very important reactions. Good bit of information there. Okay? Maybe you like by video because you can watch at your leisure, you can pause, you can rewatch, etc. Okay? And then we'll see what type of questions come up. 2 additional ways to hydrate an alkene other than aqueous acid. and then adding H's to alkenes to convert them to alkanes, hydrogenation. Stereochemistry of each of these reactions is very important. Stereochemistry comes from your mechanism. If you understand mechanism, you can predict stereochemistry. Okay, so that would be probably our Wednesday lecture. But this Wednesday instead we'll start stereochemistry. So I basically flipped those two. We probably would not start stereochemistry until Friday if we were to do this lecture on Wednesday. Okay? But I didn't want to do stereochemistry by video. I think this was better by video. Okay, I think we're ready to get going. Let's see. Any questions about material? Yes?
What will lab report be due if we don't have lab on Thursday?
When will what be
The
due?
formal lab report? The last one?
Okay, I don't want to answer it for the third time today. Have we already answered that twice already? Okay. All right, so I'm not going to answer it for a third time. Did we not hear it? When's the bromination lab report due?
Next Monday.
Yeah? Okay, guys. Good to go? All right, give me a yay.
Yes.
All right. Okay, any other questions? Good to go? Yeah? All right. Epoxides. All right, it's a very common type of, we call it a functional group. It's a cyclic ether, right? It's oxygen bonded to 2 carbons. It's a cyclic ether. Remember ring. Gets its own name, epoxide. Also called an oxirane. You don't need to know that epoxide. Actually, in Organic 2, we'll look at the chemistry of epoxides. They have their own unique chemistry because of the strange ring. Okay? Unique type of ether. Here we're learning how to make them. We typically make them from alkenes. Reacting with what? A peroxy acid. Okay? Condensed. One extra oxygen here. Most common is MCPBA. Should be in your textbook. Mechanism should be very similar. The 2 oxygens. All right. Now just the 2 bromines. Bromines, though, is schizophrenic. It has to be polarized somehow. This is polarized because of the carbonyl. Pi bond, very polarizable. That leads to partial plus here. Electrons being pulled. In the end oxygen is partial plus. And so these electrons are attracted to it. Here we go. Pi bond attacks oxygen and kicks off the other oxygen. That's what the arrows mean, right? What does that give? New bond to oxygen. Okay? New bond to oxygen. The H is on the oxygen, right? It's there. Lose bond to carbon, it is now a plus. You think this is actually formed? No, it's not, because the new group has a lone pair. When the new group has a lone pair, it's going to immediately back bond. Some books will show it right here. These electrons are coming in here as soon as these electrons go out. I don't combine all these arrows, and I've told you that before. It's actually strictly more correct. Do this, but just make sure you say it's not actually formed, because this next step happens at the same time, and when this back bonds, what do you get? You get this structure, because it just back bonded, and the oxygen is now positive. See the similarities in all our reactions. Okay? At this point, which is analogous to a bromonium ion, yeah? Everybody see your bromonium ion in lab last week when you added the bromine? Did you see it? You had to look quick. Yeah? And then the bromide came in backside. Did you ever see that? Yeah? Okay, see the, okay. The difference is this can't go neutral by losing an H, and so something ends up attacking here. maybe another bromine, or maybe water if you got water present. But nobody had water present last week, right? You had a dry flask? Okay, but if water's present, attack where? Here, kick that off. That's how the bromine goes neutral. It gets the bonding pair back as a lone pair. This thing can go neutral by losing an H in an acid-base reaction. Is there something that can take the H? Yes. What do we generate right here? This left and became third lone pair. That's what left up there. This can turn around and take an H, and the oxygen can get its lone pair back by taking this bonding pair. And all this gives what? It gives a neutral oxygen plus this carboxylic acid. And there's your product, and it can be made and it can be isolated. It's called an epoxide. Okay? This is your acid. The peroxy acid has lost an oxygen. Okay? There used to be another oxygen here. It has lost an oxygen. The alkene has gained an oxygen. It used to be double bond here, but now it's an oxygen to each carbon. So it's really just a transfer of a single oxygen. Epoxides. Pretty straight mechanism, pretty straight outcome. Here we go. We have an alkene, MCPBA, common peroxy acid. What is that there? Dichloromethane. Okay? Also known as methylene chloride. All right. What is that? What did you use that for last week?
Solvent?
Solvent. It's a common solvent. Okay? You're never going to see it react with anything in, I think, organic 1 or organic 2. It can, but it's typically a solvent. You need to get used to seeing solvents. And when you recognize solvent, they're inert. That's by definition. You don't want solvent to react. Sometimes they will, and it will be a unique thing, and we'll call it a solvolysis reaction. This is just solvent. Ignore it. What do we got? Alkene, MCPBA. What does that give? Okay, with your reactions, there's a little memorization. People say you can't memorize in organic chemistry. That's true. But you can memorize a little bit. You got to have some prompting. An alkene reacts with MCPBA or peroxy acid to give what? There you go. That's just sort of memorization. There's not a lot of learning, deep learning there. Is it okay? An alkene reacts with bromine to give what? A dibromide. You made one in lab last week. An alkene reacts with chlorine and water to give what? A halohydrin. Okay? These are just quick, okay, what do reactions give? And you're developing a toolbox. This is also good for note cards. Okay? So, what are we making here? An epoxide. What are we going to do to the alkene? Each carbon becomes bonding to an oxygen. Okay? So in terms of just predicting product, each carbon becomes bonding to an oxygen. Bam, bam. You want to put lone pairs there? Go ahead. There you go. Product. In terms of predict the product, it's pretty darn straightforward. Do we expect any rearrangements in this reaction?
No,
No, why?
because the H is not being attacked, or carbon is not being attacked.
You're not attacking H+. That's a specific reason. More generally, there's nothing that's formed. What's not formed? There's no carbocation. Do you see a carbocation in the mechanism? Wait a minute, there's one on the board, but that's not actually formed in the mechanism. That's just Stevens drawing it on the board because he thinks it's useful to help you understand, right? There's no carbocation here. The first intermediate is what? Right there. Since there's no carbocation, there's going to be no rearrangement. So, okay, there we go. Stereochemistry. We do have a chiral carbon here. And when I start, it's going to be racemic. R and S. You can just have that in your notes for now. There you go. You make that epoxide. What we got below? Got an alkene. What is this? It's just another way to show a peroxy acid. Okay? So what type of product are we going to get here? Epoxide. There you go. You show the product. But see, that right there, assessing the reaction and saying, okay, this is an epoxide, that's step one. Next would be, okay, what's the mechanism here? In case I'm asked the mechanism question, to show the mechanism. But also, what's the stereochemistry? Because when you have rings, you often have more defined stereochemistry. And it's also easier to show. I'm going to show it without stereochemistry. Bam. That's a 6-membered ring. And now we formed a 3-membered ring fused to it. That's it. But see, both of these carbons are now tetrahedral. The two bonds here to the oxygen, are they cis or trans? They got to be cis. And so we can show this with this back and the bond to the oxygen. The two bonds to the oxygen forward. And after we were asked to show full stereochemistry, keeping in mind that the two carbons are tetrahedral and thus 2 in the plane, 1 forward and 1 back, that's how it would look. Why are they cis? Well, here's the first answer is, you can't have a 3-member ring trans. Okay? Here, I'm 1 carbon. Or I'm the oxygen. Here's 1 carbon, and here's the other. Carbon, oxygen, carbon. Aren't the two carbons bonded together? Aren't the two carbons bonded together? Here we go. Oxygen. I'm the oxygen, and here's the top carbon, here's the bottom one. Aren't they bonded together? So they got a bond. Okay, I can't, that looks like they're right next to each other. Pretend I'm holding a stick and they're connected. And there's the 3-membered ring. 1, 2, like I got another arm between them. Okay? What if the other carbon was over here? Can they bond? No. No, they have to be on the same side to bond. Now they're front. I mean, it's like this. If considered this carbon and this carbon, they're both bonded to oxygen. The oxygen is over here. It's like this. They're both forward bonding to the oxygen. That's why I got them forward here. Okay? If the oxygen's over here, 1 carbon can't be bonded to it and the other carbon going back. If it's going back, it wouldn't be bonded to the oxygen. The oxygen is forward. Both bonds to the oxygen are forward. It's like that, looking at you. I'm the oxygen. Both bonds have to be forward. By default, the methyl is back because 2 in the plane, 1 forward, 1 back. Okay, it has to be. But you're also going to get enantiomer. What is the enantiomer? Enantiomer is mirror image. Okay, what is the mirror image going to look like? That's where everything is switched. The enantiomer is going to be a methyl back, and each bond to oxygen, methyl forward, and each bond to oxygen back. This is the enantiomer. A lot of times we'll just say structure plus enantiomer. Here I drew the enantiomer. The enantiomer is where everything is, all your projections are reversed. Okay, question?
Isn't that the exact same thing though?
It's just, like, how is that?
We haven't gotten there yet. It's the exact same thing because it's the exact same connectivity. And if you named it, it would have the exact same name. Stereoisomers only differ by a stereochemical descriptor. Okay? It's like this. Aren't these the same thing?
Yes.
No.
I mean, no, those are different. They're located
Well, you said yes because it's analogous.
Right.
They're both hands, so yes, they're both hands. But no, only this one will fit into the right-hand glove. This one will not. These are enantiomers. They're the same, but they're just reversed. They're mirror images. Okay? If this looks in the mirror, over there, what does it see? It's going to see that looking back at it. Mirroring. But they're different. Mirror images that are different, enantiomers. We'll get there. Right now it's in your notes and you can ask questions like that. They're different. It's like making two hands. If you're manufacturing hands, are you only making a right hand or are you making both? It depends on how you want to set up your factory. If you got a process that gives both hands, then you're getting two different products, right? It's like that. You're making both hands. It's actually hard to develop a process where you only make one hand. Okay? We'll talk more about it. Those are enantiomers. This is shown very generically with no stereochemistry. That's shown with stereochemistry. In both cases, though, the bonds to the oxygen are cis, same side. They have to be. You cannot make a three-membered ring with the two things trained. How are these things going to bond together? If these are bonded, they have to be on the same side. Yes? It's easier to show stereochemistry in rings. Down here, you can try this on your own, or maybe we'll do it product here. If you don't show stereochemistry, it's easy. Just take these two carbons and hook them to an oxygen, right? Peroxy acid. Is this alkene stereogenic? Top one, bottom one, are they stereogenic? Yeah, they're both stereogenic, right? Okay. If you have an alkene that's stereogenic, you need to do something a little bit differently. That alkene up there was not stereogenic. That was pretty easy. We didn't have as much stereochemistry up there. Here you have more stereochemistry. Turn this. And draw the alkene like this. The two groups here are trans. The ethyl and the methyl are trans on the alkene. I've just turned it and they're trans. Okay? Here we go. I'm only going to do one thumb. Here everything's in the plane. See? The thumb is in the plane on the board. If I turn my hand like this, now the thumb is doing what?
Facing the board.
Now it's going back. That's all I've done here. I've taken the alkene, okay, and I've turned it. When you turn it, one group, pretend I have a pinky here, okay? Thumb up, pinky down. Are they trans? Thumb up, pinky down? They're trans. Now I'm going to turn it this way. Now the pinky is doing what? Coming towards you. And the thumb is going away from you. Now I can show the pinky is bolded and the thumb dashed. All right? Here they're just flat on the board. That's all I've done here. Okay? They're trans here on the board, but now they're trans here, but now I can show dashed or wedged. That's very powerful because we're halfway home to getting product. Okay? No book is going to do it this way. You want my recommendation, turn the alkene before you do anything else. Now again, this is the first time you're hearing it. But in a week, we'll have thought about it and practice it, and we'll do this a couple of times. Now, I'm going to not do mechanism, but do thinking. What happens when I do the reaction? Don't I connect these two to oxygen?
Mm-hmm.
So I'm going to get rid of the pi bond and make cyclobond to oxygen. All right? Power of turning it is I'll draw my, there we go. Let's make the alkene. Flat on the board, it's a little turn here, yeah? Flat on the board. There's another here. It's a face though, okay? It's planar. Okay? Do it like this. Now the faces are top and bottom. And the pi bond reacts with the oxygen straight up, and then it back bonds straight down. And you end up with straight up and straight down, and we can draw the oxygen straight up. And we can also draw the oxygen straight down. And these are your two products here. And what's the relationship between these?
Enantiomers.
Yeah, those are enantiomers. Now we didn't reverse anything. That's because we flipped the ring. The backbone is not the same. Whenever we say you can just reverse everything like we did over here, you have to keep the backbone the same. Then you can reverse things. For your notes here, the main thing here is stereogenic. We turned it, then we put our new thing there. In the plane, straight up or straight down. You can try that on your own. Basically, this is sort of precursor to stereochemistry coming up. Question?
What would happen if you made that vessel dashed and vessel folded out? Would that have changed? And you made one of the other one dashed and
If you did that, it would be this. I can get the enantiomer here by switching projections, as long as I keep the rest the same. So you're saying if I switch projections? Made this dash, made that bolt, that'd be switching all projections. If you did that, it should be the enantiomer. Well, that's the enantiomer.
oh,
Going from what you want to draw versus that, all I've done is turned it over. Because if you turn it over, okay, right now the thumb is back. If I do this, now the thumb is forward. But see, if I do that, okay, let's consider up or down. Up, down. But see, the oxygen also needs to flip down. Okay, so you can get to the enantiomer different ways. Okay, synthesis of cyclopropanes. I've already erased it, but the key thing that we can notice from the previous reaction was the starting material for that reaction we did cis or trans?
Trans.
It's trans. Product was it cis or trans? Now the product has a ring, and on the ring we can look at the groups coming off the ring. The ring was the epoxide. Were the group cis or trans coming off of the epoxide?
Cis. Remember.
Oh, coming off the nutrients.
No, they cis or trans. One is bolded and one is dashed. That would be trans, right? Okay. The alkene was trans. Product was trans. All right. It had no time to change. Why did it have no time to change? Because of what? Yeah, it's more than that. A carbocation rearrangement would not really affect that. It would be something different. Let's see. This is not the same alkene. Trans. Bam, transition state. Ring. There's no time for it to rotate. There's no time for it. It starts trans and then it's trans here. It can't rotate. There's no time for it to rotate. There's never a chance when it can rotate. That's different from a rearrangement. A rearrangement typically refers to a carbocation rearrangement. That's a skeletal rearrangement. That involves like an H shifting or an alkyl shifting. Cyclopropanes. A three-membered ring that's all carbon. Carbon, carbon, and new carbon. So we got two carbons here. We just want to bond these to one additional new carbon. And that would give a cyclopropane. Yeah? Well, these can be made as well. And cyclopropanes are actually fairly common in drugs. Two different ways to make these from this carbines. Ch2 Carbine. A carbene is a divalent carbon. Okay? Divalent, two bonded carbon and a lone pair. What's the charge of this carbon? Charge of that carbon, how many electrons does it own?
4.
It owns 4, it's neutral. Wait a minute, I thought on day 1 we said if it doesn't have standard bonding, it would have a charge. Is that carbon standard bonding? No. Does it have a charge? No, of course, there's exceptions to everything, right? That's an exception to that statement. Okay. Carbines, they're known structures, known entities, compounds. It's neutral. It's fairly unique. I've shown it here. A lot of times you show them with two charges, a plus and a minus, net neutral. That's because it has kind of dual character. It has carbocation character, but it also has carbanion character. And so showing the two charges just sort of reinforces that in your mind. It's net neutral, and you don't have to show any charge. Question?
What happens to that N2?
We haven't done anything with it yet. What N2? Here?
Oh,
We haven't done anything yet. So that's a carbene. Okay? The Ch2 carbene can be formed from this guy, diazomethane, Ch2N2. All right? Right there. Here's your Lewis structure. Now it has two formal charges. It's also net neutral though. And if you heat this thing, first off, you've got to be careful because it will explode. It can be uncontrolled. But if you heat it in a controlled manner, entropy will take over. This nitrogen would like to go neutral. It can go neutral by saying, okay, carbon, Of course, that's bonded to carbon, right? Okay, carbon, I love you, but I'm taking the electrons and leaving. Okay? All right? All right? I love you, but I'm taking the kids and we're going. Okay? All right? 2 electrons are coming with me. What does that give? The 2 electrons are with the nitrogen, but guess what? That's all neutral. And this is nitrogen gas, N2. What did we form? Well, we formed a carbene, because when that's gone, it's just carbon with a lone pair and 2 H's. But guess what? The carbon is now neutral. Why did the carbon let the nitrogen take the kids and leave?
The pusher.
What was good about the carbon? It went from minus to neutral. Now, it's quite unusual, but we can say, well, at least it's neutral, and over here it was negative. So there's some rationale for doing this. The biggest rationale to me is what? 1 molecule breaking into 2. And so entropy driven. You heat it, entropy, heat magnifies entropy. So heating is going to cause this to happen. Okay? Once we get the carbene formed, then the alkene, okay, some other reactant, you know, maybe the neighbor or something, what type of reactivity does this have? It's neutral. Why would an alkene attack something neutral?
Partial positive.
It's got a lone pair. It doesn't like a lone pair. What's the hybridization of this? How many regions around it?
3.
3. It's sp2. 1, 2, 3. What type of bonds do you see to that carbon? Sigma bond to H. Sigma bond to H. Lone pair. What else is here? P orbital. It's empty. Does this carbon have an octet? No. Would it thus like electrons?
Yes.
Yes. So while it's not charged, it would like electrons. What do we call something that likes electrons? Yeah, a carbene is electrophile. It's electrophilic. Okay? But if we look at this positive, it's like the alkene attacks the positive character. Okay? And it's actually added into this empty p orbital. So the electrons go attack the carbon. We make this bond, right? Carbocation. Do you think this is actually formed? No, why not? Because the new thing has a lone pair. And when it has a lone pair, what's it going to do immediately?
Back bond.
Back bond. And that happens over here. We can show this is back bonding, okay? You're a carbene. I'm going to attack, you've got a lone pair. As soon as I attack you, what are you doing? You're attacking me. Bam! Here we go again. Bam! Do it like this. You're a lone pair. Now, bam! You see that? As soon as I come here, you're coming here. These happen at the same time. Do I have to keep saying that? It's consistent with previous reactions. Okay? As this comes out here, these electrons are coming in here. I'm just doing it separately, yeah? And what do you get when that happens? How many H's on this carbon? 2. It's there. How many intermediates in this reaction starting with this point? 0. The alkene reacts with the carbene to give what? Product. It's just a transition state. You don't think that's actually formed, do you? No, it's not actually formed. It's not actually formed. Okay? Once you form your carbene, it reacts to give that. It's just a transition state, no intermediate. There you go. Do you see the consistencies, though, in the previous reaction? Previously, we had an oxygen that back bonded. It had to lose an H to go neutral. The carbon doesn't have to lose an H. It's already neutral. Consistencies. Working with diazomethane, we're not going to be doing it. It's too dangerous to work in lab with first semester organic students. Okay? We need to wait till you're like 8th semester organic. Okay? We still need to work on keeping caps on reagents first. Okay? Saw a lot of, not a lot, saw some of this last week. All right? All right? So until you prove you can put caps on your bottles, then you can't, until then, before you can move on to diazomethane. All right? Keep working on the caps. All right? A much easier way to make carbines is the dichlorocarbene. You're going to have 2 chlorines here instead of H's. This is easier in lab. Chloroform, hydroxide. Chloroform, the H is somewhat acidic. Hydroxide will take an H, acid-base reaction. We can generate the carbanion plus water. Here, this is a lot like diazomethane. Nitrogen left. Here, chlorine leaves. And if this chlorine leaves as chloride, what are you left with over here? Carbon 2 bonds in a lone pair. A dichlorocarbene. Why would this happen? 1 molecule going to 2. Minus on carbon, now minus on chlorine. Doesn't that seem better? Okay, we get this. Then the alkene can attack. You think that's actually formed? Back bonding, what do you get? There you go. A dichlorocyclopropane. These can be made using chloroform and hydroxide. And there's a couple for you to try on your own. Okay, let's see where we're at, guys. Next reactions are the ones from the video. A number of drugs contain cyclopropane rings. Okay, all these contain Cipro. It's actually a very common ring in drugs, even though it's small and strange. Can be made. Carbines. Carbines are occasionally seen other places. Here is an example in drug metabolism. The drug Paxil. When it's metabolized, this carbon is converted to a carbene. So that's formed in the body. Okay. And then oxymercuration. Here are my notes from the video. Basically, the alkene reactions, there's a good bit there. See the consistencies. 2 common types of reactions for these predict products. Okay. Here's an alkene, here are reagents. What's the product going to be? And when you show products, we will have stereochemistry. And that's what we're going to be moving into now. The other type of question with your reactions is mechanisms. Okay. Given a starting material and a product, everything's given, and you ask, okay, show show a mechanism using your curved arrows to show all electron movement. All right? Two common types of reactions. And you'll see plenty of those in the workbook. Okay, stereochemistry. You have handouts today, yeah? Here's your outline, and here's a big paragraph from me with an introduction, important terms, etc. Of course, you've got your chapter in your textbook. And then we'll be moving along. You can see the outline. We'll start here and move ahead. Optical activity. We'll be doing that in lab next week. The other handout, we have some warm-up questions, types of questions you should be able to work when we're done with the material. More types of questions. Chiral carbons. How many chiral carbons in this drug? And then miscellaneous items for to look at as we move along, including the very important example of thalidomide. These two compounds are mirror images of each other. They're enantiomers. Okay. This drug was developed for morning sickness for pregnant women back in the late 1950s. Unfortunately, once it started to be produced, manufactured, the wrong enantiomer was manufactured. Instead of making the right hand, which was supposed to be the one made, manufacturing made the left hand. And the left hand led to severe birth defects, babies born without limbs, such as no arms, or small just appendages, flippers, and that's showing some of the children there. Those were the ones that survived. Many babies did not survive, stillborn, etc. This was eventually, the issue was eventually resolved. There was a nurse, an American nurse, that helped show what was going on here, and President Kennedy awarded her a medal. This mainly took place in Europe, some in the United States, but it was largely in Europe in the late 50s and early 1960s. So chirality is important, enantiomers do matter. Stereochemistry is very important. Have a great day, guys. See you on Wednesday.